Good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video we're going to be talking about electric potential in more detail. So electric potential is related to potential difference, but is not exactly the same. Related but not the same. Alright, so if you recall from the previous video, or previous lesson I guess, we had one of the examples talked about two charged plates that were parallel to each other, called a parallel plate capacitor. So one of the plates will be charged positive and the other plate will be charged negative. And then we'll place an electric field between them. So as we recall from a previous lesson, the electric field lines go in the direction that a positive charge would go in. So that's why the lines are drawn going from the positive end to the negative end. Now, if we place a charge here, so let's say for argument's sake, we place a positive charge in the electric field, where would this positive charge have the most potential energy? Well, that would be around here. If we place the positive charge closest to the positive plate, the amount of repulsive force that it feels is going to be the greatest here. Because if you recall, the electrostatic force is given by this equation, kq1 q2 over r squared. And as this number gets smaller, the amount of force gets larger. So if I place my positive charge really close to the positive plate here, there's my positive plate here. If I place this charge really close to it, then the electric force is going to be really, really large. Electric force is large. Okay. If I place the positive force here, okay, the force of repulsion is going to be much, much smaller because it's trying to get attracted to here. Okay. So the most potential energy you can argue then would be around here. Largest potential energy. Largest potential energy. Because it has the largest amount of repulsive force when it's right beside the positive plate. That large amount of repulsive force will translate into a large amount of potential energy. Because in a roundabout way, you can say, because work is related to force by this equation. So if this number is really large, then there's a large potential to do a lot of work. So there's a large amount of potential energy. Now, in the previous video, we talked about something called potential difference. So potential difference is the amount of work needed to move a charge from one point to another. And we gave the equation in the previous video. It's not quite the same as this, but it was very, very similar to this, where the potential difference, so that's this one here, potential difference is work done to move a charge from point A to point B. In a previous lesson, we discussed this or described this as force times distance divided by Q. And they're the same, because if you notice here, this is work, and then this is a force times the distance, so that's also work. Okay. So this quantity of potential difference is really just how much work, so that's this, how much work does it take to move a charge from point A to point B. The larger the amount of force or the larger the distance, the more work, therefore the more potential difference. Okay. Generally speaking, we call this potential difference just voltage. So you're going to hear this term a lot, potential difference and voltage, and they're going to be used quite interchangeably moving forward as we talk more about electricity. Just remember, potential difference, this is voltage. Usually called volts, and the units are joules per coulomb or volts. All right, so joules per coulomb represents its base definition of energy per charge, and then we just call that the volt or volts. So what follows now is just going to be a bunch of examples. So I think there's 5 of them, so there's a lot of examples we're going to go through. The first two are, I think, relatively straightforward because they're just going to be rearrangements of our potential difference equation. So for example, here, 1a, how much work is needed to move a 1 microcoulomb charge across a potential difference of 12 volts? So let's give myself some more room. So our equation then is potential difference or voltage is work divided by charge. So here we're asked how much work is needed to move this charge. Well, using this equation, I can rearrange it to show that work is equal to voltage times charge. So if I know that my potential difference is 12 volts, and I am going to multiply this by the charge of 1 microcoulomb, 1.0 times 10 to the negative 6. This gives me a total amount of work of 12 times 10 to the negative 6, or 1.2 times 10 to the negative 5. And this will be in, this is work, so this will be in joules. There we go. So the amount of work needed to move a 1 microcoulomb charge is 1.2 times 10 to the negative 5 joules. So not a lot of work needed to be done, not a lot of energy. So moving microcoulomb charges across these potential differences doesn't require that much work. All right, on to example 2, or so 1b, I guess, 1b. Okay, so here we have a 1 microcoulomb charge. This time we're going to calculate what the potential difference is. We are doing 25 joules of work in order to cross this potential difference. So again, I think relatively straightforward. Let's give myself some more room to work. All right, so here again, this will be another arrangement of our original equation. So potential difference is work divided by charge. So here I'm asked to find what's the potential difference. Well, we know how much work we're doing. We have 25 joules of work. We have a 1 microcoulomb charge. Let's write that down as 1 times the negative 6 coulombs. Doing our division, this will be 25 times 10 to the 6 volts, and simplifying it, 2.5 times 10 to the 7, and this will be in volts. So this potential difference is quite a lot. So this is about 25 million, 25 million volts. Let me check that. All right, so just checking to make sure I did my math correct. 25 divided by 6 negative to the 10. There we go. Oh yeah, 25 million. Okay, I was right. I didn't do my math wrong. That's good. There we go. So yeah, so 25 million volts. Okay, so that's quite a huge potential difference to move a simple 1 microcoulomb charge across it. Now, I'm going to go back to, I guess, the previous example where we had our previous example here. I think the answer was along the lines of 10 to the negative 5 joules of energy, right? So this is a very small amount of energy, so very small. And in some cases, because we deal with such small amounts of energy, it's actually not that useful to describe the energy in terms of joules. So instead, what we're going to do is we're going to describe the energy in a different unit. Okay, and that unit's going to be called the electron volt. Because in electricity, we tend to deal with a lot of electrons, and so the electron volt is just another unit of energy that we're going to use to help us along. This is actually quite a useful unit in nuclear physics. Nuclear chemistry uses this unit as well. So there's a precedent for it. Okay. Now the electron volt, and this is something that will mess up a lot of people, is it's a unit of energy, not a unit of potential difference, which is interesting because the volt is a unit of potential difference. Okay, so the electron volt is not a unit of potential difference. Now the reason it's not is because we define the electron volt as the amount of energy that an electron gains when we move it through a 1 volt potential difference. So basically From our equation of voltage equals work divided by charge, we basically set our voltage to 1, and we set our charge equivalent to the charge of 1 electron, which we defined previously as 1.60 times 10 to the negative 19 coulombs. So the electron volt just ends up being 1 times 1.6 times 10 to the negative 19, and that's how much energy. So that gets us this. That's how much energy 1 electron has when it moves through a 1 volt potential difference. Okay. Now again, the reason for this is because the reason where this unit is used is because in a lot of cases we deal with a lot of individual electrons. So describing the energy of the electrons in terms of electron volts will actually make a little bit more sense as opposed to describing it in terms of actual joules. Because each electron generally has a very small amount of energy. So if we define them in terms of electron volts, it's a little easier to work with. Okay. So the electron volt is the energy electrons gain when they move through 1 volt of potential difference. So if I move an electron through 2 volts of potential difference, the electron would basically have 2 electron volts. If I move it through 3 volts, the electron would have 3 electron volts worth of energy, and so on. Okay. So when working on at small scales and when you can actually deal with individual electrons, the electron volt is a much more convenient unit. Okay. Similar to how on the opposite end of that, when we measure the energy that a household uses, we tend to use the kilowatt hour as a unit of energy as opposed to the joules, because the joule, as far as like house usage goes, the amount of energy is really high. So we just create a new unit, and that's the kilowatt hours. And we'll discuss that later on as we study electricity. All right, so let's go through some examples of how we can convert from electron volt to joules and vice versa. Example 2a. In this example, it's going to talk about how much kinetic energy can an electron gain if I move it through 750 volts of potential difference. Okay, so we're talking about an individual electron. And if I use the definition of an electron volt, well, 1 electron volt is the energy gained in 1 volt potential difference. So if I have a potential difference of 750 volts, then it makes sense then that 750 volts of potential would equate to 750 electron volts, right? Because for every volt of potential difference, an electron will gain 1 electron volt of energy. So if I'm going through 750 volts of potential difference, my electron would gain 750 electron volts worth of energy. Now, if I express this in joules, well, 750 electron volts, how many joules is that? Well, every joule of energy, let's do this properly actually. All right, so it's 750 electron volts worth of energy, and we know that for every 1 electron volt, we are going to generate 1.6 times 10 to the negative 19 joules. So we just cross multiply and divide in this ratio. So we get 750 electron volts times 1.6 times 10 to the negative 19 joules. This will give me, okay, so 1.6 times 10 to the negative 19 times 750, a really small number. So 1.2 times 10 to the negative 16. 1.2 times 10 to the negative 16 joules of energy. All right, now compare this to the number, say 750 electron volts. They both express the same amount of energy, but the 750 electron volts is a much more convenient expression The number is just cleaner, easier to work with. And then you can always convert to regular joules if you ever really wanted to figure out how many joules of actual energy that is. But in a lot of cases, the 750 electron volts is perfectly acceptable. All right, example 2b. So suppose we have 1000 electrons, so 1.0 times 10 to the 3 electrons, all crossing a 1 volt potential difference. How much energy has been gained by the electrons? Let's get some more room. Alright, so here we have 1000 electrons moving through 1 volt of potential difference. And the first part expressed as electron volts will be a lot easier because, okay, if I have 1000 electrons moving through 1 volt of potential difference, well, each electron would have 1 electron volt of energy. And if I have 1000 of them, well, this makes sense that, okay, if I have 1000 electrons moving through 1 volt potential difference, then this makes sense that I have in total 1000 electron volts, right? So again, that's because so an electron volt is the amount of energy electrons gain moving through 1 volt of potential difference. So if I have a 1 volt potential difference and 1000 electrons, it makes sense that I've got 1000 electron volts, okay? Now expressing this in joules, well, if every electron volt is 1.6 times 10 to the negative 19 joules, then I just multiply those together, and the amount of energy I get is 1.6 times 10 to the negative 16 joules. There we go. All right, so the electron volt is really handy because if you understand what the electron volt means, then you can say, okay, well, it's easy enough to calculate the energy in terms of electron volts because I just say, okay, how many electrons do I have? How big is the potential difference? And I just multiply the two together to get me the number of electron volts. So as an aside, this will actually work the same way. Like, let's say I have, let's call this a 2C. Let's say I have how much energy does, I don't know, let's say like something odd, 320 electrons have going through, say, 2.5 volts of potential difference. Okay, well, you can make the same argument. Okay, well, if each electron, if one electron goes through this difference, it's going to gain 2.5 electron volts of energy. So if I have 320 electrons going through it, then it makes sense that the amount of energy I have will just be 320 electrons times 2.5 volts, and that'll get me the number of electron volts. So that would be volts 320 times 2.5. Yeah. 800, so 800 electron volts. And from there, you can convert it into joules if you felt like it. Okay, but the initial calculations are relatively easy because, okay, I can express my answer in electron volts, so there we go. Might as well just leave it that way. How do you go about calculating electric potential energy? Well, I already showed you one way. You can calculate electric potential energy as force times distance, but you can also calculate electric potential energy in a slightly different manner. So if you recall from earlier, Coulomb's law gave us the electric force was K Q1 Q2 over R squared, right? And work, as we know, is force times distance. So let's say I multiply this by a distance. In this case, the distance would just be R. Then this would create a work equation that would be equivalent to K Q1 Q2 over R. There we go. So this equation is the electric potential energy that is between two charges. And all we really did was we took our work equation and we took our electric force equation and we set them and then we just substituted one into the other, and now we get this new equation. So that equation is the electric potential energy. And Let me just erase this so it's easier to read. There we go. So this equation here calculates the amount of potential energy between two charges. So this here, electric potential energy, that's what this is K Q1 Q2 over R. And it's very similar to the potential energy of gravity. If you recall, a gravitational potential energy was G M1 M2 over R. That's the same thing. And if we sort of analyze this in the same way we did gravity, if we make R equivalent to infinity, then the potential energy is equal to 0. Because at infinity, the amount of force is really, really minuscule. So the amount of potential energy is also relatively minuscule. So let's go through an example of how we can use this equation. So example 3, what is the electric potential energy between two 1 microcoulomb charges that are that many meters apart? So I think that distance I chose, I think, is on the scale of atomic nuclei, I think. Yeah, it's very, very close together, regardless. All right, so we can calculate electric potential energy. Here's our equation. Electric potential energy was K Q1 Q2 over... I actually don't remember Coulomb's constant. Let me look it up quickly. All right, so Coulomb's constant is 8.988 times 10 to the 9. Sometimes people will just shorten this to 9.0. 8.988 times 10 to the 9. We have two 1 microcoulomb charges, so 1.0 times 10 to the negative 6, 1.0 times 10 to the negative 6, over, and we have a total distance of 5.0 times 10 to the negative 11. Now, here's something I didn't mention in previous examples, is that hopefully you all remember your exponent rules, because you can make some of the initial calculations right away. Like for example here, all of these exponents, so that 10 to the 9, 10 to the negative 6, 10 to the negative 6, you can simplify them all together and you get the following, 10 to the negative 3. And the 8.988 times 1 will just be 8.98. Here we have 5.0 times 10 to the negative 11. And again, you can use exponent rules to simplify these exponents. So 8.988 times 10, this is negative 3 minus negative 11, so to the 8. And what this does is it allows you to sort of gauge kind of how big the answer is going to be. Okay. The other thing it allows you to do too then is that in your calculator, all you really need to do is do this calculation. And then you don't have to worry about exponents during your calculation. 1.8, I guess, times 10 to the 8, and this will be in joules, right? Because we're calculating potential energy. There we go. And then we ask ourselves, does that answer make sense? Well, if I have two positive charges very, very close together, I should have a relatively large answer. Okay. For those of you who are in class and remember how I can sort of estimate the order of magnitude, this is how I do it. Simplify exponents using exponent rules, and you can get a rough idea of how big your exponent should be. It also helps eliminate calculator error, because then all you have to do is this calculation in your calculator. You don't have to worry about any exponents, which is kind of cool. Anyways, there you go. So if I have two 1 microcoulomb charges about 5 times 10 negative 11 meters apart, they will have this much potential energy. Okay. Now this is really interesting, because if you think about it, how close are protons to each other inside your atom? They're much closer than this number. Much closer than this number. Which means how much energy is actually stored between two protons sitting right beside each other. Kind of think about that. It's really, really interesting. All right, let's move to the next example. All right, so here's an equation. This is another way you can calculate electric potential. Because voltage, electric potential difference, is the amount of energy per charge, we can redefine it as the amount of potential energy per charge. So this definition is kind of just a redefining of what voltage means, because we know voltage is work per charge, but then we also know from previous studies that work is really just a form of potential energy. So we can say voltage can be potential energy per charge. Now, some of you might even take that a little bit further and say, well, we've discussed in previous classes that work is also equivalent to kinetic energy, so can we say that? We probably could, we just don't normally talk about it that way, because electricity tends to, well, that's not true. Electricity does move, but in terms of electricity, we tend to worry more about how much energy is stored per charge. So you will use this, okay? Now, when we think about it this way, and we talk about the energy per charge, and we take that equation, so the electric potential energy equation, and we put it into here, we get the following. So electric potential energy was K Q1 Q2 over R. And we're going to divide this by one of the Q's. Like, it doesn't actually matter which one. This Q will cancel out one of these Q's because it means the same thing. So this is where we get the final equation of K Q over R. Okay. So this equation here describes the potential energy of a charge Q in the potential difference. Usually that potential difference will be caused by an electric field, or it's caused by, actually no, it'll always be caused by an electric field. So this is why the questions you can use this equation for will always be basically if I have a charge and sitting in a potential or in an electric field, how much potential energy does it have? We can use this equation if I know the voltage. Okay. For example 4, how much work is needed to bring a 4 microcoulomb charge from infinity to a point 2 meters away from a 20 microcoulomb charge? We have a 20 microcoulomb charge, and we are bringing towards it a 4 microcoulomb charge, and we're going to set them 2 meters apart. So here, well, we know that work is a change in energy. So by extension, we can say that any change in energy we can classify as a change in potential energy, or we can classify as a change in kinetic energy. Since we're dealing with electricity, it's going to be a change in potential energy. So the potential energy we know, change in potential energy we know is basically what your final potential energy is minus your initial potential energy. And since we are bringing a charge from infinity, this means our initial potential energy is going to be 0. So our final potential energy is then calculated using the potential energy equation K Q1 Q2 over R. So we have our two charges, and as a reminder, K is 8.988 times 10 to the 9. So we'll just calculate this out. 9, 20 microcoulomb charge, and a 4 microcoulomb charge, and trying to bring them to within 2 meters of each other. Simplifying my exponents, I get the following, times 10 to the negative 9 minus 6 is 3. And then this one ends up being 8.988 times 20 times 4 divided by 2. So this is 359 times 10 to the negative 3. I can simplify it 1, 2 this way. So this is 3.59 times 10 to the negative 1 joules. And the two significant figures, 3.6 times 10 to the negative 1 joules. So if I want to drag a 4 microcoulomb charge towards a 20 microcoulomb charge and have it sit 2 meters away, I will need to exert about this much energy. Now this question sort of illustrates the fact that, again, work is a change in energy, and that change in energy can be translated as a change in potential energy, or in some cases it might be a change in kinetic energy. So in this example, it's going to be 3 parts to this example. We have 2 microcoulomb charges placed 1.5 millimeters apart, held stationary. How much electrostatic force is exerted on each charge? How much potential energy exists between the 2 charges? And if one charge were let go, how much kinetic energy could it possess? Okay, so this example kind of brings together all of the Coulomb's law stuff we talked about over the last couple of videos. So part A asks us how much electrostatic force is exerted on each charge. So we can calculate electrostatic force as force equals K Q1 Q2 over R squared. K again is 8.988 times 10 to the 9. Q1, both charges are 2 microcoulombs, so that makes things easy. Positive 9. We have a 2 microcoulomb charge and another 2 microcoulomb charge, and we are separated by 1.5 millimeters. All right, simplifying things a bit, exponent will be, times 10 to the negative 6, I think. 9 minus 6 is minus 3. Minus, oh no, it's not, it's going to be times 10 to the 0, I think. Yeah, that's right. 9 minus 6 is minus 3. Oh, so 3. 3 minus 6 is minus 3. Minus 3 minus 3 is 0. There we go. Okay. And then the rest of it, 8.988 times 2 divided by 1.5. So this is 23.968. This is approximately 24 newtons. All right, so that's A part. Okay, B part asks us how much potential energy exists between the 2 charges. Well, this one's easy because we know that we can calculate the potential energy as we normally would, K Q1 Q2 over R, but since we know that potential energy is basically work, and work is force times distance, we already have the force, so we can just calculate it as force times distance. So we'll use the 23.968 times, how far apart were they? 1.5 millimeters. So 1.5 times 10 to the negative 3. So this will be times 1.5, 35.952 times 10 to the negative 3. Proper significant figures, this will be 3.5952 times 10 to the negative 2. And if I go to 2 significant figures, this would be about 3.6 times 10 to the negative 2 joules. There we go. And finally, C asks us, right down here, if one charge were let go, how much kinetic energy could it possess? Well, I know how much potential energy it has. So the maximum amount of kinetic energy based on conservation of energy has to be the same as the maximum amount of potential energy. So makes sense then that at most I can have 3.6 times 10 to the negative 2 joules of kinetic energy. So this last bit kind of brings together all the force and work stuff we've talked about over the last couple of classes, I guess. Well, not really a couple of classes, but kind of reminds us of the energy stuff we talked about earlier this course, and then little bits from Physics 11 as well. Okay. So to recap things, work is really nothing more than energy. And you can also think of work as changes energy, and that change in energy can either be change in potential energy or change in kinetic energy. And then we just gave you more tools now to calculate electric energy, or electrostatic energy, sorry. Electrostatic energy was kq1 q2 over r squared. And then you can calculate electric potential energy, so potential energy electric as k q1 q2 over r, and then we just switch those around to help you guys figure out some other things with regards to energy. Okay, so there you go. So with that said, you should be able to complete the assignment here if you have your textbooks, and this will draw this unit to a close. If you have any questions, you guys all know how to contact me.